All right, so we're going to look at some quadratic functions. And we've seen this before, probably in our first year of algebra in high school. And we're going to be dealing with some vertex stuff. And the vertex is basically the maximum or minimum value of your function. In this case, of your quadratic function, it is the absolute max or the absolute minimum. So we have two forms for a quadratic function. I put formula, but I meant function. So let's read function. The first one is f of x equals ax squared plus bx plus c, where a, b, and c are integers, and the value of a cannot be equal to 0, because if it is, it's no longer a quadratic function, it is a linear function, or it could be a constant function, which is still a linear function. So we've seen this form before. That's in the form of a quadratic trinomial. So once again, we should know this form. That is quadratic trinomial. However, when it comes to graphing these quadratic trinomials, we want to have the function in a different format. We want to have it in what is called the standard form of a quadratic function, or the vertex form of a quadratic function. And we want it in this form because we can be able to identify some characteristics such as the vertex, which can then help us sketch the function, which also provides us, like I said before, with the maximum or the minimum value, but then also the axis of symmetry, which lets us know how to draw these functions. I want to remind you guys that a quadratic function, its parent function is an even function, so there is a mirror symmetry in respect to the y-axis. If you translate that function, the symmetry will no longer be in respect to the y-axis, but there will be a symmetry still existing, and that symmetry depends on wherever the vertex moves to. Okay, so here are some things that I want to get off before I look at the first couple of problems. So the limitations of the general form, it's difficult to determine the vertex, and the sketch may be inaccurate. So that's why we want to have a standard form. If the value of a is positive, which means it's greater than 0, then the function will be a relative minimum at hk, and the function opens upwards. That should make sense. If a is positive, the function opens upwards, which means there'll be a lowest point. If the value of a is less than 0, which means it's negative, then the function opens downwards. And if your quadratic function opens downwards, that means there will be a maximum point. The axis of symmetry is the x-coordinate of the vertex, such that x equals to h. The maximum or the minimum value of your quadratic function is the k value. The domain for a quadratic function is all real numbers because a quadratic function is a polynomial function, and a polynomial function has no restrictions in the real world. The range has a lot to do with the maximum or minimum value. The range has a lot to do with a. If your a is negative, we know the function will have a maximum value. And because the function is continuous, it will go down forever on both directions. So the range in interval notation will go from negative infinity to the value of k, and k is the maximum y value. If the function opens upwards, which means a is positive, then that means the vertex is a minimum point, which means that will be the smallest y value of k for the function. The range would go from k to infinity. All right. A lot of talking. Let's get into the first problem. Number 1 says graph the function f of x equals x squared. then graph the function g of x equals to x plus 2 quantity cubed. Reread again, x plus 2 quantity squared, then minus 3 on the outside. And remember that we can use function translations for that one. So let's do a quick sketch of x squared. If x is 0, then the y is 0, because 0 squared is 0. When x is 1, 1 squared is 1, y is 1. When the x value is 2, the y value is 4, because 2 squared is positive 4. And that's good enough for me. But notice, when x is negative 1, negative 1 squared is positive 1. Negative 1 times negative 1 is positive 1. And when x equals to negative 2, the y is 4, because negative 2 squared is negative 2 times negative 2. That is positive 4. And there we go. And also we can do 9 as well. That would be 3, of course, but no need to really get into that. Let's sketch this a little bit nicer. At least show that it does pass through 9 as the y value when x is negative 3 or positive 3. Okay. And as you can see, before I move on, this function has no negative in front of it, so that means the a is positive. This function has a minimum point. The minimum point here, the vertex, is 0, 0. 0, 0. This function has a minimum value of 0 when x equals to 0. If you notice, this is symmetrical in respect to the y-axis. Let's put that a little bit bolder, actually. There's a line of symmetry on the y-axis. I'll put it in dotted lines. And every value on the y-axis has an x value of 0. So we can say that the axis of symmetry, AOS, axis of symmetry, is x equals to 0. So I'm just showing you some of the key features of this function, of this basic parent function. This is a polynomial function, so the domain is infinite. It's all real numbers. And as you can see, for the range, the smallest y value is 0. That's the vertex, and that's included. That's a closed point. The function goes up on either end forever. So that's going to approach positive infinity. Okay. I did that for a reason, because I want us to understand and see how things will work when we perform the translations and how the vertex switches and what else changes. The domain doesn't change, though. The domain is the only one that's going to stay the same. G of x equals x plus 2 quantity squared minus 3. From the last set of videos, when you're adding inside the parentheses, this adding inside the parentheses means 2 units left. And when you're subtracting outside the parentheses, this means 3 units down. So we're going to translate the graph f of x equals to x squared, 2 units to the left and 3 units down. Move every point 2 units to the left and 3 units down. So I'm going to represent that on the new graph in this green color. Let's start off with the point of negative 2, 4. We're moving it 2 units to the left, 3 units down. That's going to be the point of negative 4, 1. The point of negative 1, 1. Sorry, yeah, negative 1, 1. We're going to move that point 3 units, 2 units to the left, and then 3 units down. That's going to be the point of negative 3, negative 3. The point 0, 0, 2 units to the left, and 3 units down. Let me be a little bit careful here. I feel like I'm not graphing this correctly. Sorry about that. I have to recheck this one. 2 units to the left, 3 units down. That's going to be negative 3, negative 2. Negative 3, negative 2. Okay, take this point here. 2 units to the left, 3 units down. This will be the point of negative 2, negative 3. Take the point of 1, 1. 3 units to the left. Sorry, rather 2 units to the left, 3 units down. The point of negative 1, negative 2. And the last point, 2 units to the left, 3 units down. That's going to go to the point of 0, 1. And then we're going to sketch that function. Okay, I can't sketch the function then. And this function is our function g. This is g of x equals x plus 2 squared minus 3. Rough sketch, not a good sketch. All right. Notice here, our vertex is different. The vertex, which I'm going to put back in red, is now negative 2, negative 3. It still opens upwards. So that means the minimum is negative 3 when x equals negative 2. That should make sense because the axis of symmetry should move as well. Our axis of symmetry, our AOS, not AOC, our AOS is x equals negative 2. The domain has changed. Or rather, the domain has remained the same. Excuse me, the range has changed. Domain is still all real numbers, but the range is different. Because we moved every y value down by 3 units, the range goes down from negative 3 to positive infinity. The smallest y value is negative 3, and it goes up on both ends to positive infinity. When I say axis of symmetry, if this was a perfect sketch, like on Desmos or the graphing calculator or the TI on the phone, the axis of symmetry will be this line, x equals negative 2. Now, before I end this video, I want us to make a relation between the vertex and the function, because the function is f of x equals to x plus 2 squared minus 3. And the vertex is the point of -2 comma -3. You gotta be very careful here. You need to remember, the sign is different when it's inside the parentheses. It's not the same for the y. So we can say change the sign of our x value only. Y stays the same side. All right. That is it for this first part, or this first video. I think I'm going to do 3 more videos on this topic. But for the most part, I'm going to say this one and then probably the third video are the ones that are super important. All right, guys. I'll catch you around. Take care.